Hi, I'm Lukas Schamriß from a PhD student in Munich, and I'm a colleague of Louis in the group of Peter Rabel. And I also would, first of all, really thank you much for giving me the opportunity to talk here about my PhD project, which is about one of the topics Louis already mentioned in his talk, namely, can we use a similar setup as he presented to generate a Bose-Einstein condensate in a waveguide? And so this means really a Bose-Einstein condensate of microwave photons. So let me get started. Why are we interested in that hardware of superconducting qubits? As you all know, it has rapidly been developed during the last years, mainly being driven by the goal of achieving quantum supremacy using computing, so performing quantum algorithms on such superconducting chips, where basically qubits are implemented by using the bosonic modes on the chip, which have a strong nonlinearity and therefore behave effectively as two-level systems. We now want to think differently about these bosonic modes and really treat them as photons, but photons which strongly interact, which is the same as the strong nonlinearities as are being used in quantum computing. I show you two setups here to make this a bit clearer. So here you see two setups basically consisting of a microwave resonator. So this really hosts a microwave bosonic mode. On this side, this is basically the yellow part, and here this is this long array of Josephson junctions. And on one side of this resonator, then there's a mirror. Really, you can think of a cavity. On the other side, there's a nonlinear element. And on the left-hand side, this is the snail, which is basically shown in the inset, and that gives rise to a three-body term in the Hamiltonian. And then here it was used to engineer this dry-squeezing. And on the other side, it was used to engineer interactions in a multimode setup, where then effects of many-body localization could be probed. Now if you think about how can we use these interactions for many-body simulations, we first of all see we have the strong interactions, which we need. Second, we also realize the superconducting hardware tends to have a relatively low loss compared to other photonic platforms, which is a big advantage. However, and that's the problem Louis mentioned, we don't have a way to thermalize these photons without changing the photon number. So I formulate this here as we basically don't have a phononic bath in the sense to have low energy degrees of freedom below the energy of the level of the microwave photons. So I mean, you know these pictures now. If you thermalize massive bosons, it works via interactions. And since the bosons have a mass, these interactions can't change the photon number. Photons, however, on these chips always thermalize via absorption and emission. And as we tune down the energy, every mode of the photons thermalizes individually, leading to zero occupation in the limit. The main question I want to ask now is, can we use the strong interactions we have at hand at these chips to overcome this issue? So basically to stabilize the photon number, or vice versa, the chemical potential of the system. And yeah, it turns out in the optical regime, we have heard a lot about this during the week. And there exist many ways of achieving that. In principle, you have the same problem, but either you can use the mass of excitons to stabilize this photon number, or in microcavities use dye molecules, which then transmit a photonic bath in principle. And in this talk, I want to show you a circuit implementation of a mechanism which can achieve the same thing for microwaves, and then show you some numerical results which show that we really can achieve something like a condensate. And in the end, we also want to interpret that as photon refrigeration. And the basic idea now is we use a waveguide, so basically the resonator element I showed you in the experiments before, which has a number of k-modes, so really standing wave in this waveguide. So maybe an important difference to Alberto's talk. In our case, nothing propagates through that waveguide. That's really a resonator, multimode resonator in that case. And we use another bosonic mode, which is strongly dissipative, as in Louis' case. So this will be this waste in the end. And the interaction is designed in a way that there are three operators which work in a way that they take one photon from a higher mode, put it into the next lowest mode, and scatter off the energy difference. So in a diagram, this would look like that. Photon comes, is re-emitted into the waveguide at a lower energy. And now if you take into account the dissipation of the bath mode, this should lead to an effective energy current out of the waveguide, but importantly, in a way that the total photon number in the waveguide can't be changed. So a photon can never really leave the waveguide. And this should in principle lead to what we want, namely a reduction of the energy or respectively temperature, but at constant photon number. Yeah, and I directly go to the implementation we have in mind. So on the left-hand side, you see this blue part, which is basically a discretized version of a waveguide. These waveguides typically can have a quality factor up to 10 to the 6 and fundamental mode frequencies down to 60 megahertz. And then at one end of the waveguide, we couple our nonlinear element. So you see here the snail in circuit language. This basically consists out of Josephson junctions. So this is really the source of nonlinearity in that model. And these snail couplers basically are an element capable of 3 and 4 wave mixing in the systems at relatively strong interaction strengths. And then on the right-hand side, you see the waste mode. So this is really just an AC resonator in electronics language. So it's basically a harmonic oscillator. But this one needs to be strongly dissipative in the end. We need to remark that also the waveguide will be dissipative. We can't get rid of that. And so this whole system really sits in an environment of around 10 millikelvin in the end. From the circuit, we can derive a Hamiltonian. So first of all, you see the K modes at equal energy spacing, the waste mode. And then the term which is important, which comes from the snail coupler. This is basically a potential in terms of the flux degrees of freedom, which is something like positions in the circuit. And it depends on an external flux, which penetrates this loop. So if you think about the super pairs, which can, the Cooper pairs, which can go around the circle, they will pick up a phase if you apply a chemical potential, essentially. Apply a magnetic field, which goes through the loop. And this potential acts on the phase difference between the waste mode and the waveguide. And this local phase couples all the K modes, basically. So this sum over K modes is equal to phi 1. And then if we look at the form of the potential after fixing all... Yes. After fixing all the internal parameters of the snail, we basically see that in first order to the external flux, so we assume it to be small, this is proportional to a sine of phi, which is the difference of these fluxes. And then if we go further to rotating wave approximation, we see that the linear order of the sine doesn't contribute, it's not resonant, and only the third order gives rise to terms which are exactly of the form which I presented before. And this is mainly due to the choice of the drive frequency of this time-dependent external flux, which matches the energy spacing of the waveguide with this waste mode frequency. Now we know the Hamiltonian. And now basically the last step is to go from the Hamiltonian to a master equation by tracing out the waste mode, which is the bath in our system. So basically that means all the B degrees of freedom will vanish here, and we set the waste mode to a thermal occupancy throughout the talk. The jump operators look like, in Lewis' case, they're quadratic in the waveguide degrees of freedom. And if we then additionally add the loss, this gives two terms at different rates, which contribute to the master equation. That's all about the analytics. Now I want only to summarize the parameters in the system to make it a bit easier to follow. So we have this waveguide, which couples to the temperature at rate capital gamma, which is small. And on the other side, it couples with the rate g coherently to the waste mode, which itself is strongly coupled to the environment at rate small gamma. And deriving the master equation basically amounts to interpreting this part as an effective bath, which couples at rate g squared over gamma now. So those are the two rates which will play a role now. And what you will see soon is that this bath effectively has a lower temperature, which comes exactly from that detuning of the level spacing in the waste mode. So it's an effective lower temperature. And we can basically arbitrarily tune this temperature down by increasing the flux frequency. And if we look now at the steady state of the waveguide, those are the three parameters which will play a role. So the ratio between the two coupling strengths, the temperature, and the fraction which defines this lower temperature. Now I will come to the results. We use a mean field theory to solve the master equation numerically, which basically amounts to neglecting correlations between the occupancies of all the K modes. And then if you look at the time evolution of the occupancies, we see that there are terms, which currents between the modes, which I denote by J, and the loss term proportional to capital gamma. Now we basically find two ways of thermalizing the system. First one is the trivial one, where every mode thermalizes individually, and we get, as we expect, a Bose-Einstein distributions for the occupations. In the spectrum, you can see this is the dotted line. And then we also have the engineered way of thermalizing the system. These currents between the modes basically establish a detailed balance condition between the occupations. And the form of it resembles very much the kinetic equations we saw on Wednesday. So you can either draw a correspondence to the ASIP versus ASIP physics Louis presented, or see that at kinetic equations which thermalize the system. And if those left and right moving parts add up to zero, this basically gives a steady state, which is again a Bose-Einstein distribution, but importantly now at the effective lower temperature, since these currents are driven by the lower frequency of the waste mode. So this may be one of the main messages of the talk, that this engineered dissipation can transmit a lower temperature onto the waveguide. Also, what is important here, we see for the first time a chemical potential. This is basically because the particle number is conserved in this process and is a free parameter basically set by the initial condition of the time evolution. And only if we now go to both processes at the same time, we see that the detailed balance is weakly broken and we have a net current from the higher modes towards the lower mode. And the distribution we find now for different ratios of the two thermalization mechanisms give rise to non-equilibrium distributions as expected. But importantly, as we tune down the dissipation, we see that the lowest mode occupation rises further and further. And this is basically connected to the way how this dissipation fixes the chemical potential. And we can understand this if we just sum up all the NK dots. That basically means that gives rise to the evolution of the total particle number, which must be zero in the steady state. And that tells us that K times NK minus K times NK thermal, and summed over it, is the same. So basically saying the energy of all these lines I draw here is the same. And this is just basically a funny effect of this ohmic bath coupling, that the kth mode dissipates straight K gamma, not just gamma. And this we can use to understand that as we go towards the lower temperature, we suppress the energy in higher modes, and all this energy needs to be captured by the lowest mode. So basically, actually, as we cool, we increase the particle number and not even just keep it constant, which is really due to the physics of this ohmic bath. And we can just study this analytically in the continuum limit. So the level spacing is zero, and we assume that all the modes are effectively thermalized, and then look at the condensation fraction and really see for any cooling fraction which is below 1, this condensation fraction really jumps to 1. So basically we see a kind of first order phase transition in this parameter of the model. We then also looked at the truncated Wigner approximation, which, as Louis said, gives basically rise to a beyond mean field approximation of the system, from which we can also extract particle number fluctuations. And we see that in the lowest mode, the G2 of 0 basically drops below 2, so transverses from a thermal state to something in between a coherent and a thermal state, which is basically another signature of the condensation. Now, as we basically have seen that we can get something like a condensate in the system, we also asked, can we use this property of having a lower temperature to effectively generate a refrigerator for photons? And there we encountered a problem that as we tune down via the dissipation from the higher temperature to the lower one, we have a lot of non-equilibrium distributions for which it is not clear how to assign a temperature to them. And we struggled around a bit, but then came up with a way, basically by asking what if these photons were really bosonic atoms in a gas, and then they basically do evaporative cooling, so they equilibrate starting from such a distribution with the conservation of energy and particle number. And I have to stress, we don't know about a way to really implement this, so this is really just a theoretical tool at the moment. But then basically these conditions uniquely fix a chemical potential and the effective temperature to which the photons would thermalize. I can plot these distributions on top of the non-equilibrium ones, and you see basically we have the feature we want. We go from an effective high temperature distribution to a low temperature distribution which approaches this threshold for the effective temperature as we turn down dissipation. And that we now used in our model. So we fixed here parameters to something which we think is realistically available on the platform. So dissipation of 10 to the minus 4. We go to 1 Kelvin, which is round about the highest temperature we think we can use, because afterwards the superconductivity will break down. And we use the longest waveguide we can have just to increase the cooling effect, so to say. And then what we tune is this fraction of the lower temperature, and a plot by which fraction we can decrease with respect to the physical temperature. And you see, first we basically can thermalize the modes to an arbitrarily low temperature until we saturate at some point. And this saturation can be understood because it basically comes from the distributions becoming non-equilibrium. So at that point the dissipation is not sufficient to thermalize these modes. The big problem which you encounter is if you look at how many modes we can use. So the yellow line is for just 2 modes, and then we increase the mode number in the waveguide. And you see this cooling effect rapidly decreases. And we can understand this problem if you look back at the distributions and realize that the point until which that is the modes thermalized with respect to the cold temperature scales exponentially with the dissipation. So if I want to thermalize linearly more modes, I need to decrease the dissipation exponentially, which is just not possible on the platform. And we can then also consider the limit of many modes and basically ask the question, if we really couple to all the modes at once, how far can we get in the cooling? And it turns out that we are basically limited by a cooling factor of 5, which is not enough. And we thought about a way around this, basically by adding to this chain of thermalization processes also all the non-local ones. So we have all-to-all coupling of the modes. And we also have an idea how to implement that, but that's work in progress so far. So this brings me to the conclusion. So I presented a simple implementation for this thermalization. I showed you that this really leads to condensation of the photons in the waveguide, and I showed you how to interpret this really as a photon refrigerator. And the goal is, first of all, I mentioned, to increase the efficiency. There we have some ideas. What would be also interesting for us to understand the state of the photons in the waveguide in an ensemble way. Basically, it turns out from the truncated Wigner approximation that the state seems to be lying between a canonical and a grand canonical ensemble. And we're not very sure about the physics of the state and would like to understand more. And in the end, we would like to understand how we can use the state in some way to also thermalize really an interacting many-body system like a Bose model. And with this I would like to thank my supervisors, Peter and Louis, and also all the team of the WMI, which you can see here doing some sports. Thank you for your attention.